Hello. Although there are many clustering algorithms, the three main ones are more dominant: K-means and its variants, hierarchical clustering, and density-based clustering. So today we will talk about K-means and its variants with respect to clustering algorithms. So let's start with an example. In K-means clustering, assume that we have to segment customers for marketing reasons. We want to come up with 3 campaigns. Can we group the clients for targeted campaigns? So we have a number of clients or customers. We would like to actually cluster them such that we can actually put these customers in different campaigns, and we decided that we will have 3 different offers, and we are now trying to see how we can actually put these in these clusters. What we know is, let's say we know the age, and then they also visit our website. We somehow keep track of how many times they visited our website. So assume that these are the guys and also ladies we have, and we have age and visit information. So she has 42 as the age and visited 7 times. And now I like to put people that are similar with age and visit together in one cluster. We know that it's not going to be the same, so we will want to get as close as possible. So I can probably look at it and see that this person here, the first one, is similar to maybe her, which is close in age, but has the same visit number. So this is again, as you see, it's pretty difficult to even understand and visualize in mind. But let's put in 2-dimensional graph and let's look at the segments. So we have age and we have visit count. So if you look at this graph, you can clearly say that these can be grouped together and these others can be grouped, and each have their own segment. So in segment 1 we decided to actually put these guys together. In segment 2 these are together, and this is segment 3. So visually we can actually see that we can cluster them. This is clustering. So what I would like to do is we only look at 2 dimensions here. We may have other information in addition to age, visit, but we might have many more information. The objective is here is to use as much data as we can and bring them as close as each other, considering all these dimensions. So this is a partitional clustering approach. We have K specified, that's the number of clusters, and each cluster is associated with a centroid. So we have a center, and around the center we have data points. Each point is assigned to the cluster with the closest centroid, and the basic algorithm is very simple. So we start with select K random initial centroids. We don't know first these clusters, although you see that visually it's not visible to the algorithm or the software code. So we will start with some random K initial centroids, and we will assign each point to the closest centroid. And once we do the assignment, we will recenter these centroid points that we actually started with. So initial points are going to be moved, and once we see that the centroids don't change, we will stop the algorithm, but until that we will continue. So it is a recursively it will call until we don't see much of a change in centroids, or the points are not changing anymore. So there's a point where it will stop. It will converge basically. So let's say I happen to start with 3 centroids, that I happen to know that these are 3 clusters. So you can probably see we have a cluster here, we have a cluster there, and we have a cluster here. But initially when I first start, I just start with some random points, and it happens to be on the top side of the data, and it's, let's say here, these are plus signs are initial centroids. So if I look a point down here which has -1 and 0y value, it is closest to the centroid. Apparently you can clearly see that it's not going to be close to any of these, so that's why I actually mark that as green. So there's a blue point right down here which is closer to this centroid than that centroid, so therefore it is actually marked blue. And again, these are closer to this centroid. These points, all the red ones, are close to this centroid. But now forget about these centroids. I did the assignment, and I will do one more time, and I will see if there is any change in centroid. Then I will keep continue, but if I see no change, then I will stop and quit. So what I will do next is actually using these data points only, these green ones, blue ones, and red ones. So let's look at the green center point. It's going to be somewhere around here, right? And blue is going to be somewhere around here, and red is going to be somewhere around here. So red is not too far off at this moment, but clearly these blue and the green ones are going to move. So let's do that. Oh, it moved. So in the second iteration, I compute my new centroid based on the green point's medium point, or the mean. Now I will actually, since I have the point is here, now I'm going to recompute all these points again, find the closest centroid, and then mark its color. So this is marked, and now I'm going, okay, this is not going to change, the one at the bottom, but some of these that I used to have some greens here, now they actually switch color to red, and they became close to this point, because as this moved on, these are now moving to that point. Again, both greens and blues are switched to red colors, and my centroid moved. So next step, I will have my centroid moved again, and I will reassign the points. Okay, you see it's moved again. So I have 5 points left here now, a few points for blue and as well as green. And again, once again, the centroid center point is going to be somewhere here and somewhere here. Now it is going in the right place, right? Now this is becoming the red, and these are becoming the colors of desired colors. Once this is 4th iteration, 6th, 5th iteration, and 6th. So if you look at it, 1, 2, 3, 4, 5, really no change in the 6th iteration. Between 5th and 6th, no point change, but maybe there's a slight change in center points, but not a significant change. So that's when I stop. I hope you understand. So it's a simple algorithm. It just moves iteratively and reassigns points after it recentered the centroid. This is also showing you the steps together. Over time, you can see not much change in these points, as you see between 5 and 6, but most of the change happened in the first few iterations. So initial centroids are often chosen randomly. We can actually do other things to have a better algorithm, but let's start with random option first. Therefore, centers are assigned or chosen randomly. Clusters vary from one run to another, so there may be some changes, but hopefully it will converge over time, and it won't be much of a change. But again, I will show you where this is going to not work really well. So there are cases, but initially the centroid is the mean point of the cluster. Initially centroids are chosen randomly. How do I measure closeness? I can clearly use Euclid distance, but there are also other similarity measures. We have a topic on that. We have cosine similarity, correlation, and others that we could use to measure the distance, or meaning it is close. K-means will converge for common similarity measures that we just talked. Most of the convergence will happen in the first few iterations, and we won't stop until relatively few points change cluster, or you look at the centroid, and if it doesn't change much, then you stop. What's the complexity of this algorithm? It is big O and K LD, number of points, number of clusters, number of iterations, and the number of attributes. So it is sort of a super polynomial algorithm. It can be expensive, but not that bad either. It's a basic algorithm. Most common measure is sum of squares of errors to measure the goodness of cluster. So we come up with a cluster at the end, then we can measure through these measures. For each point, the error is the distance to the nearest cluster, and we sum these errors. As you see in this SSE, it's sum of squared errors equals to distance square, and you sum them for each cluster. Simple algorithm. X is a data point in cluster Ci, and Mi is the mean representative point for the cluster Ci. Given two sets of clusters, we prefer the one with the smallest error. So if we have two clusters, we would like to choose the one with which produces less SSE. But what you could do is, one easy way to reduce SSE is to increase K, the number of clusters. But again, if we have too many clusters, that's also not desired. This is also sometimes not the objective of this clustering. So we want to sort of summarize data, and therefore we want to reduce the number of clusters in many applications. So that's why we can still have a good clustering and a low SSE than a poor clustering with high K. So if you don't have the algorithm right, then you may actually end up with more K with a higher SSE too. But again, that is the alternative. So you would like to have reduce the SSE for optimum clustering. So how many clusters we need? So often we choose 3, 4, 5, but how do we decide that? It sometimes comes from the business that they want to have maybe 3 campaigns and that's all. But sometimes you would like to know the optimum, what you should do, looking at different customers. So if you plot summed errors with iterations, as you can see, most of the error happens in the first iterations. As we move, the error is gone, it gets close to 0. I mean, if you hit like all the points, then you have 0 error, but basically most of the convergence will happen in the first few iterations. And this is the elbow point where I have decided that I will settle with K equals 4. In this case, for instance, just as an example. So that's where you may just say, okay, I'll select K as 4. So we have original points, we may have an optimal clustering, or we have some suboptimal clustering like this. It is totally possible if we don't have maybe good start points. So K-means has problems when clusters are of different sizes, densities, or shapes, like non-globular shapes. If we have also outliers, K-means will also have problems with that. So let's look at this cluster here. We have 3 clusters. You can clearly see it by eye. But here That's not that easy. So to fit that 3 clusters, so it will actually cluster it like that using k-means. So this is a limitation. There are ways to overcome, which I will talk next, but let's look at different density. So these are higher density, this is larger, more sparse data, which will produce a large SSE. So therefore, if I have decided I will fit 3 points, the 2 will actually fit here to reduce the error, because error is a square of the distance. So with sparse points, it will try to minimize at this location. Although there are many more points here, their contribution is small. But this can change, because many more points can also bring that close to here if it is critical. Like if these are close to each other, then it will definitely try to put as many points here as possible. With non-globular shapes, really difficult to cluster, because if you put it here, it will. This is looking like as if it is a circle. Like this is where the centroid is, and that's the center point, and it has a shape, a circular shape. So I can actually cluster it like, but you can see by eye these are different clusters. But this is visually easy to identify, but algorithmically with using k-means it's not that easy. So what you could do is you can use as many points as many clusters as you want to reduce those errors. Like here, instead of using 3, we use more to normalize it. Then you can actually maybe look at these sampled points. In a way, it is a sampled points, representative points, and then further cluster it. So you may do a 2-step clustering. Like here we have a situation where it is clustered here and we have more points. So these are well identified, but again I can actually merge these, because these are not far from each other, but these definitely are, again using many more points. But again, this is not going to be really easy to do with k-means. Therefore we have also other approaches which we will talk. So initially I choose these 3 initial points, and then I can converge it like this in an optimal way. But if I started with these initial points, I might end up with a non-optimal clustering too, which is not always easy to see, but it just happened to calculate it that this is it's now converging, as you can see. Not much change, like between 4 or 5. So this is also a suboptimal clustering, which could also happen. But 4 and 5th for iterations, not much changed. And with starting different initial points, I might actually have maybe a suboptimal clustering at the end. But this is part of the problem here, is we have different shapes. These are small, but this is a large. So this actually creates a problem with choosing the right centroid. If there are k real clusters, then chance of selecting one centroid from each cluster is really small. So if you happen to pick the right centroids, or at least in the right cluster, the centroids is really low. So if we have 10 clusters, using this this formula, we have a very slim chance of hitting right centroids, like having one centroid in each cluster. We may have 2 centroids in a cluster, and we may have a cluster with no centroids. So that is having one at each centroid, probability is low. Sometimes the initial centroids will adjust themselves in the right way, but sometimes they don't, which I show you. Consider an example of 5 pairs of clusters in the next slide. So we have 2 here, we have 1 here, 2 here, 2 here, 2 here. So we have total 10 clusters, 2, 2, 2, 1, and maybe one of them has 3. This might be 3 too. 2, 2, 2, 2, 2. Okay, each has 2. Looks like, yes, each has 2. So this might be fine. So it is actually hitting at the right centers, no problem. But so as you see, perfect. Starting with 2 initial centroids in one of the clusters of each of the pair of clusters. So at each pair I had 2. But what if I have a pair right here, only one, but then I have 3 in this. So in this pair I have 3 clusters, but I have none here. So likely this will not converge, as you will see now. So this is moving it here, and okay, this is fine, but then we have 2 here overlapping, so it's converging. Again, now it didn't really converge. So initial point selection can be critical. So how we actually solve this? We can have multiple runs, but again, probability is not in your sight. We can sample and use hierarchical clustering to determine initial centroids. So we do sort of a initial run, and then using some samples within that to determine. Select more than k initial centroids and then select among these initial centroids. This is most widely adopted. Select more than k initial centroids and then select among, so you actually eliminate some. Basically you choose more than k, and hopefully you will have higher chance of hitting one at each cluster, and maybe some cluster will have more, but then you will actually eliminate some of those. You can be doing post-processing, we will talk about it. We can generate a larger number of clusters and then perform a hierarchical clustering. Again, it is like here, similar to that. We have again large number of clusters. Bisecting K-means, that's another algorithm which I will also talk, which is also more robust. That is a new approach in K-means plus. Can be slower than random initialization, but very consistently produces better results in terms of error. To select a set of initial centroids, perform the following. So the algorithm is similar in some ways, but I will tell you the key here is you start with some random point at beginning, and then for k-1 steps you actually introduce a new centroid with respect to proportional with respect to its distance. Like if it is a high distance, that is a distant object, then that being selected as a new centroid is going to be high. So there's a probability in selecting, instead of randomly selecting a centroid, you select a centroid with distance being higher probability. So I'll show you that. So if it was k-means, we choose 1 for instance. K-means might choose 2 as a second point, as a second center, but in k-means plus, it will actually choose maybe 1 as random, which is the same, but then the second point is going to be the one that is the most distant in this set. So that's how it is the difference. So we have k-means can yield empty clusters. This is not always a bad thing. Sometimes we would like to actually find clusters that are useless and eliminate them, but if you are really interested in having to have 3 maybe customer segmentation, then we may want to avoid that. But here how it will work. So let's say you choose this point and that point and that point, sort of distributed randomly, and then after each iteration, okay, maybe it will actually move to here. So I'll show you. So let's say this is how it is set at the beginning. So 10 and 15, the midpoint is 12.5. 6.5 and 9, the midpoint is 7.75, 17.25 for this others cluster. So now I'm going to do the assignment again, but this time 10 is closer to this point than that point. So it 2.5 versus 2.25, which is closer to here. Then it will actually assign to this point. Again, 15 is going to be assigned to that point. Then I have this centroid, a cluster here, which with no points in it. So this might not be always desired, but sometimes, I mean, that may be perfectly fine. I can even say maybe most of the time. So, but if you are really needing another segment, for instance, what you could do is, if you want to avoid empty clusters, you can choose a point from the cluster with the highest SSE. If there are several empty clusters, the above can be repeated several times. So where I can actually, let's say I actually calculated the SSE for all these points, then I will choose to eliminate this. I'll choose, if this is higher, for instance, then I might actually put another one right here and then redoing clustering. If there is so I can eliminate all the empty ones by actually assigning a new centroid that has the highest SSE. We can also update points after we do assignments. So each assignment, centroids are updated after all points are assigned in the normal algorithm, in the basic K-means. So I have the centroid, then I update all the points assignments basically. An alternative is to update the centroids after each assignment. So as I actually put a point, I recalculate centroid and incrementally adjust. So each assignment updates 0 or more to centroids. More expensive, introduces an order dependencies, like which point you will select the next, for instance. Never get an empty cluster, that will also be satisfied. Can use weights to change the impact. So basically I can also do incremental approach as opposed to a one-time shot. There's also pre-processing and post-processing steps where we can actually normalize the data, eliminate outliers in the pre-processing step. That will actually have a more robust estimate of the clusters. Or we can actually do the processing, and after that, if we end up with small clusters that represent outliers, we may want to eliminate those. We can also split loose clusters that really add too much SSE to the overall picture. We can actually put them in other clusters, loose clusters, and even eliminate some of those loose clusters if it is not looking normal, and even ignore it. That's a typical thing that we can do in data science. We can also merge clusters that are close with low SSE. So if there are really close clusters, we may rather eliminate and then merge them as if it is in the partitional hierarchical clustering. Bisecting K-means is another algorithm that can produce a partitional or a hierarchical clustering. It can do both. How it depends on how you look at it. I will tell you about this now. First, it will select a cluster from the list of clusters, and for I equals 1 to the number of iterations, there might be a limit on how many times you will need to iterate. Bisect the selected clusters using basic K-means. Bisect means that dividing the cluster, and you finish. But how do you bisect? So add 2 clusters from the bisection with the lowest SSE to the list of clusters until the list of clusters contain K clusters. So let me demonstrate it. I think it will make more sense. This will repeat, right, until the list of clusters contain K clusters, until you reach the ideal cluster number. You keep adding centroid to the one with the lowest, with the highest, actually highest error part. You add a new point. So let's start with first cluster, and then I have, say, I have 3 cluster limit. So I will actually move to the next step. So first cluster, and the second I will just split the data as if it is normal. So this is my centroid, so I'm going to add another centroid, and this is like normal k-means, so nothing is different in this sense, but this is where it will change. So now I'm going to choose this or that cluster to actually bisect, meaning add a new centroid. So we start with full data, we divide them into clusters by applying regular k-means where k equals 2. So this is nothing different here, but then if we are going to do up to 3 clusters, we will actually continue to divide the one side with the highest error. So this has highest error, so that's why I actually omit this part, redo it. In the next step, if I were doing 4 clusters, because this has low error, then I will actually further cluster this one. This is looking like a hierarchical clustering in a sense, but also it is a partitional clustering because we are partitioning the data. So, but the method looks like hierarchical. Bisecting, I have 2 centroids. So I have a higher error in this left side, in the blue part, than the red side. So I do reassignment. I add a new point or new centroid, let's say, and okay, this part I have a lower error now. Among these 3 clusters, which has highest error, maybe I have a highest error in this side, so I'm going to further split this. If this is the case, obviously. If not, then I might actually further split this. So if this has higher, then I'll choose this. If this is higher, then I will split this one. Let's see. Okay, this was higher, obviously, so it added another centroid. It didn't change any of the first 2 clusters here and the last 4 clusters here. Next, I will actually clearly add another cluster here, like here. This may be perfectly fine. So I am now doing another one here. Obviously I'm going to add another one here. Now I'm actually going to keep adding these, choosing the one with the highest error. This should have been included here, so it must have been missed, but that's bisecting k-means example. So this is it for the clustering algorithms, k-means and its variants. We will also talk hierarchical clustering in the next lecture.